Okay, today we begin our study of rational functions, and these are the things that we're going to learn how to do. We'll take them one at a time on each of the next slides. You can feel free to pause it at any time and take notes and apply what we do on here to the paper that you're going to get in class. So what is a rational function? Well, a rational function is a function that has ratios, and so therefore a fraction. And so we might say, we just finished studying polynomials, so it's maybe a numerator of a polynomial over a denominator of a polynomial. For example, it might be like this. F of x equals x plus 1 over x minus 3. That could be a rational function. It's a polynomial on the top as well as a polynomial of some sort on the bottom. Okay, how do you graph a rational function? To graph a rational function, let's make up one here that we might want to look at a little bit. Y equals, or let's go f of x equals x plus 1 over x minus 3. You go to your calculator and do y equals, and you're probably going to want to put parentheses. Well, I know you're going to want to put parentheses around the top and then divide by parentheses around the bottom. If you fail to do the parentheses and just type it into your calculator as x plus 1 divided by x minus 3, it will only be the 1 that gets divided by the x. Clearly that is not what we were attempting to do up here, so make sure that you contain the entire numerator in parentheses and the entire denominator in parentheses. Okay, so in general, when you're graphing rational functions, you want to be able to paint a mental picture of what your calculator is going to show you, so you kind of know what to expect. And in order to do that, you have to know the general shape of a rational function. So if we have an xy axis here, the general shape of a rational function may do something like this. It might do this, and then pick up again and do this. So we kind of have a general idea of what the shape is. Now, on each rational function, it's possible to have a thing called a vertical asymptote. That'd be a line right here that the graph is going to get closer and closer and closer to on each side. As it goes up, it gets closer here, and as it goes down, it gets closer to that line here. That red line is called a vertical asymptote. And we also have on this graph a horizontal asymptote, a line right in here that the graph can get closer to. Now, interestingly enough, we can cover this more in detail when I get back, but a horizontal asymptote can get crossed, can get touched, but a vertical asymptote will never get touched. Okay, and we can cover that when we get back. But to know that there's a vertical asymptote and a horizontal asymptote, or possibly a horizontal asymptote, those are the things that we're going to spend some time trying to figure out how we find out where they're at in the next few slides. So we need a function here again, and I kind of like the one we've been using, so let's talk about x plus 1 over x minus 3. In order to find vertical asymptotes, you want to just take the denominator, whatever it is, set it equal to 0, and figure out what makes that denominator turn to 0. So here's the denominator, x minus 3, set it equal to 0, solve it, and find out that when x is 3, that makes this bottom turn to 0. Well, you never want to divide by 0. If you have like 1 divided by 0, that's an error. And when that happens, when you divide by 0, you cause a vertical asymptote to occur in that location. So I promise that on this problem, there is a vertical asymptote at the line x equals 3. Whatever makes the denominator turn to 0 is where you'll find a vertical asymptote. Okay, so let's do one more example here of finding vertical asymptotes. The plan is to take the denominator and set it equal to 0 and try and solve it. Well, and you can solve this one in one of two ways, I think, but I personally see that it's the difference of squares. And so I'm going to have x and plus 2 and minus 2. And so what makes the denominator turn to 0 is when x is a negative 2 and when x is a positive 2. So we will have two vertical asymptotes in this case, where x is negative 2 and where x is positive 2. Okay, you may take a moment and jot this information down and pause this as needed and get it into your notes, and then I will show you examples of each of these in the next on the next slide. Okay, so here's a problem where we're trying to find now the horizontal asymptotes, no longer the vertical asymptotes. But if we're trying to find the horizontal asymptotes, we have to reference this as either top-heavy, bottom-heavy, or balanced. And what I mean by that is I look at the lead terms of both the numerator and the denominator, and I see that we have an x squared on the bottom and yet only an x to the first on the top. I will call this situation when the exponent is bigger on the bottom than the top. I'll reference that as bottom-heavy. And when you have a bottom-heavy rational function, there is a horizontal asymptote always at the location y equals 0. So just recognizing that it's bottom-heavy tells you that the horizontal asymptote is at y equals 0. Okay, so continuing to try to understand horizontal asymptotes, one of three conditions will always happen in a rational function. It will either be bottom-heavy, which was referenced on the previous slide, and you'll know the horizontal asymptote is at y equals 0 when that happens. Or in this case, it is balanced, and by balanced what I mean is I'm looking at the lead term of both the numerator and the denominator, and I find that both of these have a power of 1 exponent. To me that's balanced, they're the same. And so what I reference now is I reference the numbers that are in front, the coefficients of that numerator and denominator, and I can just literally write the equation y equals 2/3. There will be a horizontal asymptote at that equation, y equals 2/3. So in review, when you have a balanced situation, you can peel the numbers right off the front, the coefficients of the front number, and y equals that value will give you the equation of the horizontal asymptote. The third and final condition for checking for horizontal asymptotes is when the function you're looking at is top-heavy. And by top-heavy, I mean reference the lead term of the numerator and the denominator and check the exponents of those lead terms. When the top exponent is bigger than the bottom exponent, then there is no horizontal asymptote. This will actually lead us to a different situation that we will address tomorrow. Okay, again, you may pause this at any point and take the notes down that I've left you here. To find the domain of a rational function, let's start with including all real numbers. So we could say that the domain of a rational function is all real numbers except a couple. And the numbers that don't get included in the domain are those where there are vertical asymptotes. Okay, so if I have the function f of x equals x minus 1 over x plus 3, we would want to check for vertical asymptotes, and that's done by setting the denominator equal to 0, solving, and finding out that there is a vertical asymptote at x equals negative 3. That means that the domain of this function is all real numbers except x equaling negative 3. Sometimes you'll see on the answer key where I've taken the extremely short way of saying don't use negative 3, and I'll say the domain, all real numbers, when x is not negative 3. So just so you understand, there is no graph where that vertical asymptote exists. So if you find the vertical asymptotes, you know exactly what the domain should avoid. I am going to show you that you can take notes on this, but I'm going to show you examples of finding x-intercepts and y-intercepts when I return. I don't think that's asked of you today to do it all, but you can take the note down if you wish. Here's another slide where finding the y-intercepts. I'll show you if you don't remember how to do that or if it's not working out for you. We can discuss that when I get back, but you can at least get the notes down so that you know kind of what you're supposed to do.